Let's do an example. A 1 kilogram rubber ball is dropped from a height of 10 meters. After hitting the ground, the ball rebounds to a height of 7 meters. If no energy was lost due to the ball's collision with the ground, how much thermal energy was generated by air resistance? Let's begin with a picture depicting the scenario. So I'll start off with the ground. I'll indicate that the ground is our x-axis. Our ball starts off at a certain height above the ground, and it will eventually hit the ground and rebound back up to a particular height. So let's go ahead and set our y-axis to be vertical. We'll assume that the ball falls straight down. So we are given the initial height of the ball, which I will define the initial height of the ball to be 10.0 meters. At that initial height, the ball starts off at rest, so I'll indicate that as being v naught is equal to 0 meters per second. Now you may be wondering why it's important for me to go ahead and label the speed. Well, we'll need to label the speed at some point, but because we have experience with conservation of energy, anytime I know that an object has a change of energy in one of its forms, so if an object is in the influence of a conservative force such as gravity, we know there's going to be potential energy, and near Earth's surface we'll need to know a reference point, the reference point being the ground and how high above the ground we are. Since we have potential energy, it's usually a good idea to indicate the other forms of energies or to be aware of them. So at that particular height, the ball has a particular speed. Well, in this situation, the speed is 0. So I am looking at the ball's state of energy at that point, knowing that it has a certain amount of potential energy and that its kinetic energy is 0. And since kinetic energy is the energy of motion, I'm indicating the speed. And so I'm kind of working ahead by just writing both the height and the speeds because I know I'll need them later. So the ball then falls, hits the ground, and rebounds. Let's now indicate what we know about the ball when it's at its final height. The ball at its final height, we will say is y equals, I'll go ahead and change that variable to h, and that is going to be equal to 7 meters. The ball's speed at that height is going to be 0 meters per second, because it rebounds to its maximum height. Now, conservation of energy, as we've learned it, says the change of mechanical kinetic energy plus the change of mechanical potential energy. Now remember, mechanical energy is the macroscopic kinetic and potential energies. And that is equal to the work done by non-conservative forces. So in order to solve this problem, we need to know what the forces are. If the forces are conservative, then we are going to look at the potential energies they contribute. If the forces are non-conservative, we're going to look at the work done by those non-conservative forces. So in looking at this problem, we know that we have the force of gravity acting downward on our object. And as our object falls and acquires speed, there is going to be a drag force, which is the force of air resistance, that will always act opposite the velocity of the ball. There are no other forces except for the time in which the ball recoils with the ground. So during that time, there is a normal force that the ground exerts on the ball. So looking at this into conservative and non-conservative forces, the conservative forces, well, we have only one. That is the force of gravity. The non-conservative forces, well, we have two in this problem. We have the drag force, which is air resistance, and we have the normal force when the ball hits the ground. This is important because since we recognize gravity to be a conservative force, we could look at the potential energy due to gravity. And since we recognize that air resistance and the normal force are non-conservative forces, we will look at the work done by air resistance and the work done by the normal force. Now, this is mostly a bookkeeping or an accounting measure. We always want to account for energy in all of its forms. So, rewriting conservation of energy, we have the change of kinetic energy. We only have one form of potential energy in the form of gravity. So this is the change of potential energy due to gravity is equal to the work done by air resistance and the work done by the normal force. Now, while the ball is in collision with the ground, the ball isn't moving. It's no longer displacing. So even though the ground exerts a normal force on the ball, the ground will do zero work on the ball. So essentially, I'm assuming something. I'm assuming that the size of the ball remains fixed. I'm assuming it doesn't change size as it hits the ground. And the reason why that's important is if it changes size, then we have to consider some level of displacement that the normal force will cause in distorting the ball's shape. Now, because it says no energy was lost due to the ball's collision with the ground, I'm going to assume that any energy that was lost would have been into deforming the ball. So since we're assuming that no energy is lost, we'll just assume the work done by the normal force is zero. That leaves us with the work done by air resistance, W sub d. So we have the change of kinetic energy plus the change of potential energy is equal to the work done by drag. But remember, the work done by non-conservative forces is equal to minus the change of internal energy. So, the work done by drag is going to be equal to minus the change of internal energy. But what does that mean? That means minus the change of thermal energy plus chemical potential energy plus nuclear potential energy. For this problem, we're going to assume changes in nuclear potential energy are negligible and changes in chemical potential energy are also negligible. So writing conservation of energy out, and I am now going to expand kinetic and potential energy. So I now have change of kinetic energy, which is the final kinetic energy minus the initial kinetic energy, plus the change of gravitational potential energy, which is gravitational potential energy final minus gravitational potential energy initial. And that's equal to the work done by air resistance, which is just the change of thermal energy. So this is 1/2 mass times final speed squared minus 1/2 mass times initial speed squared plus mass times gravity times the final height minus mass times gravity times the initial height is equal to minus the change of thermal energy. We know the final speed is 0 and the initial speed is 0. I'm also calling y is equal to some final value h. So we have the change of thermal energy due to air resistance is equal to mass times gravity, the initial height of the ball, minus mass times gravity, the final height of the ball. When I factor out the weight of the ball, mg, I see that the change of thermal energy is due, in this situation, to the change of gravitational potential energy. You could kind of see that up here in this line, that since kinetic energy, the change is zero, this is an example of potential energy, or at least a portion of it, being transformed into thermal energy. Let's go ahead and plug in numbers to see what we have now. The object's mass was 1 kilogram. The free fall acceleration due to gravity is 9.80 meters per second squared. The initial height of the ball was 10.0 meters. Final height of the ball was 7.0 meters. So when we look at this, I'm going to kind of visually do a unit check. Kilograms times a meter squared per second squared, that ends up being a joule. When I plug this into my calculator, I get 29 joules. So what this says is that air resistance changed the thermal energy of the system by 29 joules.